from the dot. That will be the force of the ground on your body. Okay? So some people will draw it like this, which is how I would not like you to draw it. You have the vector down, and then you have the vector up, and then some people will draw an additional vector up like that. I would not like you to draw it like that, because when people draw it like this in the past, some people interpret that this first vector here is the whole length, where some people interpret it just as that length. So this is not how I want you to do it, okay? This is how I would like you to do it. And then also you can show that, again, you're at rest, you want a balanced force diagram. So this force of Earth on your body is equal to the two vectors pushing up on your body. So the force of the Earth on the body is equal to the combination of the two forces up, the chair pushing up and the ground pushing up. And the chair is pushing up with a greater force than the ground, because you feel the chair more than you feel the ground pushing up on your body. So if we consider a car that is coasting to the right and it's slowing down, and we're going to draw right here as an example of how the force diagram would look for that. So again, we start with the dot, and then we always have our one non-contact force, which will be Earth. So Earth is pulling down on the car. And then what is in contact with the car? Well, the ground is. So the ground's essentially doing two different things. It's pushing up with the exact same amount of force as the Earth pulls down. So you're balanced vertically. So if the force of Earth on the car was 100 newtons, then the ground would also push up with 100 newtons. 100 newtons up cancels out 100 newtons down. And then there's also, it's slowing down, okay? That means we are accelerating. And there's also, when you rub your hands together, your hands gets warm because of friction. So if you're coasting to the right, it's not being pushed or pulled in that direction. It's like taking a shopping cart, pushing it and letting it go, and then it coasts on without you having to continuously push it. That's this example. And it's slowing down because if it's coasting to the right, friction is always in the opposite direction of the movement. So if it's coasting to the right, the friction is going to be pulling it backwards, and that's what's causing the car to slow down. And again, we draw friction with a lowercase f, and then it's the frictional force of the ground on the car. So the up and down forces cancel out, so we're balanced vertically, but we are left with this leftward force over here. There's nothing to balance out this force, so we're unbalanced horizontally. So this is overall an unbalanced force diagram, which means it's accelerating. And again, you can accelerate by speeding up, slowing down, or changing directions. So when we look at these force diagrams and you want to know if it's accelerating, we look at the forces. So if we say if we have balanced forces, then no, it's not accelerating. If you have unbalanced forces in your force diagram, then yes, it is accelerating. And which direction do you accelerate in? Well, you always accelerate in the direction of the unbalanced force. So if you have nothing canceling out a certain vector, that's the direction of the acceleration. That's the direction you're going to be speeding up or slowing down or changing directions in. And our last one, number 4, how can you accelerate? Again, you can accelerate one of 3 ways: speed up, slow down, or change directions. So balanced forces, no acceleration. Unbalanced forces, yes acceleration. And you accelerate in the direction of the unbalanced force. So again, a force is any push or pull. So this can happen when objects are in contact or at a distance in certain circumstances. So these are, again, our contact and non-contact forces. We measure forces in newtons, just like if we measure distance in meters, we measure mass in kilograms, we measure forces in newtons. So let's take a look at this Kathy and Rich example, and I'm going to give you some time to think about who you think is correct. So here we have Kathy and Rich in a classroom, and Kathy has a heavy metal ball, and Rich has a light wooden ball. And they dropped these objects from the same exact height, and they were surprised to discover that both objects reached the ground at the exact same time. And this is what Kathy and Rich said after the balls landed. So Kathy said that the force of gravity must be acting the same on both balls. Rich says, I don't agree. The metal ball weighs more, so the force of gravity is more on the heavier ball. So I would like you to think about who do you agree with and think about a reason why. And we are going to be doing a lab to prove who is correct, Kathy or Rich. So let's just do a couple force diagrams for certain objects, and then we can get on with our mass and weight lab. So for the first example, it says a book is at rest on a tabletop. So again, if it's at rest or it's moving at a constant velocity, those are the two examples that you're going to have a balanced force diagram. So here we have a book that's at rest. So we have our book, our dot, and then we always have our one non-contact force, which is going to be Earth pulling it down. So the force of Earth on the book. And then again, it's on the tabletop, and that's in our one of our contact forces. And so where it's at rest, I want it balanced. So the table is going to push up with the exact amount of force as the Earth pulls down. So that's that for that example. We have a gymnast that is suspended motionless by two ropes. So the gymnast is hanging straight down with her arms vertically up above her head. And the force is acting on the girl. So we have our one non-contact force, which is the force of Earth on the girl. And then we have two ropes. So one hand's in contact with one rope and the other hand is in contact with the other rope. So these are two different forces. Each rope is applying a force on the girl. So again, she's suspended motionless, meaning at rest. So we need to be balanced. So we're going to have, you need to ask yourself, how is the ropes pulling on the girl? And the ropes are going to be pulling up, because if the ropes didn't pull up, she would go down. And so we have two ropes. So two arrows up and one arrows down, and we need it to be balanced. So we have one vector that's half the size as the one going down. So that's going to be, we can say, the force of rope 1 on the girl. And then we're going to also have another vector. You can make your dot a little larger if you'd like. Another vector going up the exact same length and still half the size as the vector down. And that's going to be the force of rope 2 on the girl. And again, we can say that down here, that the force of rope 1 on the girl plus the force of rope 2 on the girl is the same as the force of Earth on the girl. And then our last example, an egg is in free fall from a nest, and we're going to neglect air resistance. So we have our egg, and we always have our one non-contact force, which will be the force of Earth on the egg. And then you ask yourself, is the egg in contact with anything else? And we're neglecting air resistance, so we can't say air, and nothing else is in contact with it. So this is our example. This is our free body diagram. And any free body diagram, any free fall object is going to have this exact force diagram. Okay? It doesn't matter if you launch something straight up, you drop it straight down, you toss it horizontally, you toss it up at an angle, you toss it down at an angle. It's always going to have the exact same force diagram. All free fall objects do. All right, here we have a rightward force is applied to a book in order to move it across a desk at a rightward acceleration, meaning speeding up. And I automatically see that word acceleration, and I automatically think unbalanced forces. We're going to consider frictional forces, neglect air resistance. So we start off by drawing a dot. We have our one non-contact force, which is Earth pulling the book down. Then you ask yourself, well, what is the book in contact with? Well, the book is in contact with the desk. So the desk is applying actually two forces on the book. And then also there's this rightward force, this applied force that's pushing it to the right. So first we need to know, is there anything balancing out this force of earth on the book? And yes, the table. It's not going down into the table, it's not going up off the table, so you need to be balanced vertically. So the vector up needs to be the exact same length as the vector down. So that's the force of the desk on the book. And then we've got this applied force to the right because it says a rightward force. So I'm going to draw a vector right. And again, these are qualitative force diagrams. So if you want to, I'm just going to draw essentially the same length as the arrows up and down. I don't know until we start putting numbers on these vectors. The length of them really doesn't matter unless you know one is double or half the other, then I would expect it to be double or half the amount. So this is going to be the force of, I'm just going to say P, the push on the book. And then it is accelerating to the right. So I need an unbalanced force diagram. We're considering friction. So if it's going to the right, friction always acts in the opposite direction. So friction is going to be to the left, but it needs to be smaller than the vector to the right because it has a rightward acceleration. You always accelerate in the direction of the unbalanced force. So I'm going to draw a little vector to the left. That is friction, the lowercase f, the frictional force of the desk on the book. So as you can see here, this amount of vector here cancels out with that exact same amount of vector to the right. So we'll say that, okay? Then we have a portion that's left over, all right? That portion is unbalanced, so that's why it is accelerating. And we can name this, we're going to do this in a couple slides, but this is your unbalanced force. So I'm just going to say your sigma F. That's what I usually call it. So that's what's causing this rightward acceleration. All right, for the next one, we have a rightward force is applied to a book in order to move it across a desk at a constant velocity. So we're essentially the same last problem, except now instead of it's accelerating, it's moving at a constant velocity. And when I think constant velocity, I automatically think balanced forces. So I start off by drawing my dot, vector down, which is the force of Earth on the book. I have the desk pushing up, the force of the desk on the book. I have this force that's to the right, force of the push on the book, and constant velocity, so friction must be the exact same amount as that push to the right. Lowercase f, desk on the book. So we are balanced vertically. This cancels with this, and this cancels with this. So you're balanced vertically and you're balanced horizontally. So this force diagram, if I just gave you this force diagram without any background information, you wouldn't know if it's at rest or at a constant velocity because they have the exact same force diagrams. And also again, note, when we draw force diagrams, you only draw it for one object at a time. So again, the second letter in all of these is the exact same because we're only focusing on one object at a time. All right, we'll do these two examples, a cart at rest versus a cart coasting. So a cart at rest, so we've got our dot. We have Earth pulling down on the cart, and then the cart is in contact with the ground. It's not moving, so we have a balanced force diagram, and the force of the ground on the cart is going to be the exact same amount as the force of Earth on the cart. So that's this one. So now a car coasting, so again, this is like the shopping cart example. You take a shopping cart, you push it, you let go, and you draw the force diagram once you are no longer touching it. It doesn't automatically stop the moment your hands come off of it. It keeps coasting in the direction that you initially applied that force. So we have our dot,